You wake up in a world where the moon in the sky looks the same as it did to your parents. Same craters, same dark patches, same bright scars. But the story underneath that surface has shifted. For most of your life, the main facts about the moon came from one era: Apollo and the Soviet Luna missions. Those were the rocks in every lab and textbook. After Luna 24 in 1976, no one brought back new samples for 44 years. In that time, we launched space telescopes, mapped exoplanets, landed rovers on Mars. But for the moon itself, we were still relying on the same small collection of stones. But before we continue, please subscribe to the channel to give your support. Let's continue. Here's the strange part. People kept running new tests, building better instruments, squeezing more data out of those Apollo and Luna samples. But all of it came from one hemisphere and a narrow set of sites. It's like trying to describe all of Earth using rocks from one region, then assuming the whole planet works that way. For decades, that was treated as close enough. Then China changed the game. In 2020, the China National Space Administration sent the Chang'e 5 mission to Oceanus Procellarum on the moon's near side. No astronauts, just a lander, a drill, and a return vehicle with one job: grab fresh material and bring it home. Chang'e 5 collected about 1,731 grams of lunar soil and rock. That's 1.7 kilograms, around 3.8 pounds, from a young lava plain in the northeast of that region. It scooped the surface, drilled down, sealed the samples, and launched them off the moon back toward Earth. That doesn't sound like much mass. You could hold it in two hands. But in planetary science, each gram is a data factory. You slice it thin, look at minerals, measure tiny amounts of radioactive elements, and from that you get ages, temperatures, traces of water, and a record of what the mantle was doing billions of years ago. That is why these new samples matter. They are not souvenirs. They are timestamps from a part of the moon we had never dated directly. But there's another problem hiding in plain sight. Every single rock you just heard about, from Apollo, from Luna, from Chang'e 5, all came from the near side, the face of the moon that always points at Earth. You've seen that side your whole life: dark seas of basalt, bright highlands, obvious craters. The far side, the face that never turns toward us, looks very different. It is mostly thick, bright highlands with only a few lava plains. We had detailed pictures and gravity maps, but for decades we had zero physical samples from there. We were still guessing. That gap is exactly what Chang'e 6 was built to close. In 2024, Chang'e 6 launched with a harder mission: land on the far side in the southern part of the South Pole Aitken Basin and bring material back. The far side never faces Earth, so you can't talk to a lander there directly. To fix that, China placed a relay satellite beyond the moon, bouncing signals between Earth and the far side lander. Chang'e 6 touched down, scooped soil, drilled into the ground, and loaded the material into a small ascent vehicle. That vehicle blasted off, docked with an orbiter around the moon, transferred the samples, and the orbiter carried them back in a return capsule. When scientists opened that capsule, they found about 1,935 grams of far-side material, roughly 1.9 kilograms or 4.3 pounds of soil and rock from inside the South Pole Aitken Basin. For the first time, humans have physical samples from the far side of the moon, from one of the biggest and oldest impact structures in the solar system. Now, labs can put near-side basalt from Chang'e 5 on one slide, far-side material from Chang'e 6 on another, and directly compare them. Here's the key question this raises. Are these samples basically the same, meaning the whole moon evolved in one simple way? Or are they different enough that the near side and far side have to be treated as two separate stories? This is where the details hit. The new near-side rocks from Chang'e 5 turned out to be younger than the Apollo samples, meaning lava was still erupting around 2 billion years ago, hundreds of millions of years later than we thought. The far-side rocks from Chang'e 6 formed from cooler lava, and the soil looks drier, which points to a mantle that lost heat and volatile elements faster. Put simply, one half of the moon stayed hotter and more active for longer. The other half locked up earlier. Now, scale matters, so let's put some numbers in place. The South Pole Aitken Basin, where Chang'e 6 landed, is about 2,500 kilometers across. That's the metric value that goes into models. In everyday terms, that's about 1,550 miles wide, roughly like going from New York to Dallas and back again in one loop. The moon itself is only about 3,475 kilometers in diameter, a bit more than 2,100 miles, so this one impact scar covers a huge fraction of the whole body. A collision that big doesn't just carve a hole, it changes how heat and material move inside the moon. That's why you're going to hear a lot of kilometers, kilograms, and degrees Celsius as we go deeper, because that's how the physics is actually calculated. But whenever a number feels abstract, we'll translate it into miles, feet, pounds, something your intuition can grab quickly. Metric is the standard ruler. The American system is there to give you a fast mental picture. So what is really at stake? Why should you care that China moved a few kilograms of gray dust across 380,000 kilometers, about 240,000 miles? Because those samples are forcing scientists to rethink when the moon cooled down, how long it kept erupting lava, where its water is stored, and how a giant impact may have stripped heat-producing elements from one hemisphere and concentrated them under the other. When you update that, you're not just tweaking lunar geology, you're changing the timescale we use to understand craters and lava plains on Mars, on Mercury, and on icy moons across the outer solar system, because all of those ages are calibrated against the moon. So now you're left with this. If a few kilograms of new rocks can already stretch the moon's timeline and split its interior into a hot side and the cool side, what happens when we zoom in on those samples and look at the lava itself and see just how late the moon really refused to die? How do you call a world dead when it's still pumping out lava 2 billion years after it formed? For decades, the standard line about the moon was simple and neat. The moon formed early, it cooled fast, and by around 3 billion years ago, the main volcanic activity was done. The youngest lava samples from the Apollo missions were about 2.8 billion years old, so textbooks showed a timeline where the moon was geologically active at the beginning, then slowly faded out and became a cold, solid, cratered rock. In that picture, the interior was like a cooling ember in a fire pit, fading out, not a live engine still feeding eruptions. You were probably taught some version of that, maybe not with all the dates, but with the idea that the moon was dead very early. Smooth, dark areas, the Maria, were explained as ancient lava plains from the distant past, not something that stretched far into the middle of the moon's life. The logic was, if we don't see fresh volcanism now, and our youngest rocks are 2.8 billion years old, then most of the action must have been over by about 3 billion years ago. Simple, clean, and, as it turns out, incomplete. So here's the problem that starts to push on that story. What do you do when new rocks turn out to be hundreds of millions of years younger than your previous youngest sample? Chang'e 5 landed in the northeast part of Oceanus Procellarum on a specific unit of dark lava called the Mare basalt. Before it ever touched down, orbital cameras and spectrometers had mapped this region and noticed that its crater density looked lower than older Maria, which hinted that it might be younger. But crater counts are indirect. To lock down an age, you need physical rocks and you need to measure the ratios of radioactive elements and their decay products inside those rocks. That's exactly what labs did with Chang'e 5. They measured isotopes in minerals like zircon and other components in the basalt, using radiometric dating. The answer they got was around 2 billion years, not 2.8. Not a little younger, but roughly 800 million years younger than the youngest Apollo basalts. Suddenly, the moon is not shutting down volcanism at 2.8 billion years. It's still producing lava well into 2.0 billion years ago. To put that in context, the moon itself is about 4.5 billion years old, so you're looking at eruptions that happened when the moon was already halfway through its life. That's like thinking a person retired at 40, then finding out they were running marathons at 55. The entire cooling curve you had in your head now stretches out. But maybe you're thinking, okay, 2 billion year old lava sounds cool, but how big a deal is it in physical terms? Are we talking about a tiny patch or something that really matters? The area Chang'e 5 landed on is part of what's called the EM4 unit in geological maps of Oceanus Procellarum. Using orbital data, scientists have estimated that this lava sheet has an average thickness of about 51 meters. That's roughly 170 feet. Picture a 15 or 16-story building, that kind of height, but not as a tower, as a flat blanket of solid rock spread over a huge area. In volume, the estimates for this single unit fall between about 1,450 and 2,350 cubic kilometers. In more familiar units, that's on the order of 350 to 560 cubic miles of basalt. If you took a city the size of New York and covered it with a layer of lava 50 meters thick, around 160 feet, that's the kind of scale you're dealing with. This is not just a little leftover patch. This is a major lava flow that erupted long after the moon was supposed to be geologically quiet. So what does that tell you about the moon's interior? Lava this young means the mantle, the layer under the crust, was still hot enough to partially melt, generate magma, and push it to the surface 2.0 billion years ago. For that to happen, you need a long-lived heat source inside the moon. That usually means radioactive elements like uranium, thorium, and potassium that slowly release heat as they decay, and some kind of insulation that keeps that heat from escaping too fast. In older models, the amount and distribution of those heat-producing elements were set so that the moon's mantle would mostly stop melting by about 3 billion years ago. The Chang'e 5 Niche blows a hole in that. If volcanoes are still active at 2.0 billion years, you either underestimated how much radioactive material the mantle holds, or you underestimated how well the crust and upper layers trap heat, or both. The moon did not just cool and freeze quickly. It cooled in slow motion, with pockets of the interior staying hot and active much longer than expected. And this is where the tension jumps beyond just lunar geology, because the moon is the reference we use to tell time for other worlds. Here's how that works in simple terms. When you look at a surface on Mars or Mercury, or even on some icy moons, you count craters. More craters generally means an older surface. Fewer craters means a younger surface. But to turn number of craters per square kilometer into an actual age in years, you need a calibration. You need some surfaces where you know both the crater count and the real age from rock samples. The moon gives you that because we have lunar rocks with solid radiometric ages, and we can match them to the surfaces they came from. If you then discover that one of your key calibration points, like the very young Mare and Oceanus Procellarum, is 800 million years younger than previous samples, that shifts the curve. It means that a given crater density might correspond to a different absolute age than you thought. A lava plain on Mars that you said was, say, 2.5 billion years old based on the old lunar curve might turn out to be younger or older when you plug in the updated moon data. The same goes for volcanic plains on Mercury or resurfaced patches on icy moons. So here's where you are now. One mission, grabbing 1.7 kilograms, about 3.8 pounds, of rock and dust from a specific lava flow 380,000 kilometers away, has forced scientists to stretch the moon's volcanic timeline by hundreds of millions of years, rethink how much heat its interior held, and start adjusting the age scale for other planets and moons across the inner solar system. And that raises the next bigger question that keeps the pressure on. If the moon stayed hot enough to feed lava at 2.0 billion years, and if some regions were clearly more active than others, what else can we learn about its deep interior from just a handful of these rocks, and how exactly do they record the moon's fading thermal heartbeat? So how do you read the moon's internal temperature just from a few chunks of frozen lava sitting on a lab bench? When you look at a basalt rock from the moon, you're not just seeing random gray material. You're seeing a record of the conditions where that magma formed and cooled. Different minerals only grow at certain temperatures and pressures, and they trap specific elements in specific ratios. So when scientists slice a Chang'e 5 basalt down to a wafer and point microscopes and spectrometers at it, they're basically reading off numbers that say this melt came from a mantle that was at least this hot and at least this deep. In simple terms, every basalt is a thermometer that has been frozen in time. The mineral mix in the Chang'e 5 samples, things like how much olivine, how much pyroxene, how much plagioclase, and the chemistry inside those crystals, all point to magma that formed from a mantle source still hot enough to partially melt 2.0 billion years after the moon formed. That's not a guess. That's what the mineral structures and element ratios are telling you. If the mantle had been much cooler, you would not get that combination of minerals or that style of basalt. So the first big message from these rocks is blunt. The moon's interior was still able to generate melt, move it upward, and erupt it on the surface in the late Middle Age of the solar system. That immediately raises the next question. What kept the inside of a small body like the moon that warm for that long? This is where the long tail of radioactive heat comes in. Inside any rocky planet or moon, you have some amount of heat-producing elements, mainly uranium, thorium, and potassium. Their unstable isotopes decay over time, releasing energy. On Earth, that steady decay is one of the main drivers that keeps the mantle convecting, plates moving, volcanoes active. For the moon, older models assumed a certain average amount and distribution of these heat-producing elements. And with those numbers, the mantle cooled enough that big eruptions should have tapered off long before 2.0 billion years ago. But when scientists look at the Chang'e 5 basalts, they see signs that the source region in the mantle was richer in these heat-producing elements than those older models assumed. You see this in the trace element patterns, things like elevated thorium and potassium compared to other rocks. That extra radioactive inventory means extra internal heating, and over hundreds of millions or even billions of years, that matters. It can keep parts of the mantle roughly 100 to 200 degrees Celsius warmer, that's about 180 to 360 degrees Fahrenheit, than they would be otherwise. The key idea here is not that the whole moon was uniformly hot, but that certain zones, especially under regions like Oceanus Procellarum, had a boosted heat budget. The moon's interior starts looking less like a simple cooling ball and more like a patchwork, with some areas losing heat quickly and others staying warm and partially molten for a lot longer. You're seeing the same basic physics that powers Earth's mantle, but scaled down and rearranged inside a much smaller world. Now that leads straight into another puzzle. If the mantle under the Chang'e 5 site stayed warm for so long, what was happening to the wetness of that mantle? And how did that affect how easily magma could actually erupt? Basalts from Chang'e 5 don't just record temperature, they also carry information about volatiles, things like water, carbon, and other gases that can be dissolved in magma. Detailed chemistry and mineral analysis suggest that the mantle source producing these lavas was gradually losing water and other volatiles over time. In other words, the deeper rock that fed these eruptions was becoming more dehydrated compared to earlier in the moon's history. Why does that matter? Because water, even in tiny amounts, acts like a lubricant in magma. When there's more water dissolved in the melt, it lowers the temperature at which rocks start to melt, and it makes the magma less viscous, more runny. Take that water away, and you get the opposite. The mantle is harder to melt, and the magma that does form tends to be thicker and stickier, more resistant to flowing. So you get this tension. On one hand, radioactive elements are keeping parts of the mantle warm enough to melt. On the other, the mantle is getting drier and more viscous, which should make eruptions more difficult. And yet, you still see these large lava flows at 2.0 billion years. That tells you that there were localized pockets where the combination of heat, composition, and maybe stress in the crust still allowed melt to gather, rise, and erupt onto the surface. Put simply, the interior was becoming more stubborn, but not fully shut down. You're looking at a moon where volcanism is fighting uphill against dehydration and still winning in some regions. Now, let's tie the numbers to something your brain can feel. When we talk about a mantle layer feeding these eruptions, think in terms of around 100 kilometers thickness, that's roughly 62 miles, of mostly solid but slowly deforming rock beneath the crust. It's not liquid like water, it's more like very hot, very slow-moving solid that can flow over long timescales. And that kind of material, even a few parts per million of water, meaning just a few grams of water per million grams of rock, can make a difference. It can change how easily the rock starts to melt. It can change how fast the partially molten rock can move and how easily it can squeeze through fractures in the crust. When Chang'e 5's chemistry points to a mantle that dried out over time but still managed to push out big eruptions, it's basically telling you that the moon's deep interior stayed just soft enough, just gooey enough in the right places for magma to escape, long after most models said it should have frozen solid. So, from a few kilograms of basalt, around 3.8 pounds of rock, you've now learned that the moon's mantle kept a long-running thermal engine powered by radioactive elements, that it dried out and became more viscous but still produced eruptions 2.0 billion years ago, and that its heat was not evenly spread. It was concentrated in certain zones that refused to shut down. And that sets up the next step in the story. If the interior is this patchy and long-lived, what happens in places where gigantic impacts dig deep enough to throw possible mantle material onto the surface? And can a rover actually see that with its instruments and tell you how the moon's insides are layered? How do you study a world's deep interior when you can only land on its skin? You just saw how Chang'e 5 proved the moon stayed hot and active much longer than we thought, but that still leaves a big missing piece. What is the deep interior actually made of, and how is it layered? For that, you need something brutal, an impact big enough to punch through the crust and throw deeper material up where a rover can reach it. On the moon, there is one place that stands out for that, the South Pole Aitken Basin. This basin is a planet-scale scar, about 2,500 kilometers across and up to 8 kilometers deep. That's roughly 1,550 miles wide and up to around 26,000 feet deep. It covers a huge chunk of the far side. Inside that basin sits Von Karman Crater, and that's where Chang'e 4 and its Yutu-2 rover touched down. If any location has a real chance of having chunks of mantle rock mixed into the surface rubble, it's this one, because the original impact dug so deep into the moon that it likely pulled up material from far below the normal crust. So here's the key question. If you're driving a small rover across this kind of impact scar with no drill that can go kilometers down, how do you know if you're actually seeing mantle material on the surface or just more crust that got smashed up? Yutu-2 carries a visible and near-infrared spectrometer, basically a device that measures the sunlight bouncing off rocks at different wavelengths. Different minerals reflect and absorb light in different patterns, so by looking at those patterns, you can work out what minerals are present, even if you never pick up the rock. Around the landing site, Yutu-2 scanned boulders and regolith and picked up signatures dominated by two minerals, low-calcium pyroxene and olivine. Those names sound technical, but the basic idea is simple. The moon's crust is mostly made of lighter, aluminum-rich minerals like plagioclase. The mantle, deeper down, is predicted to be richer in heavier iron and magnesium-bearing minerals like olivine and certain types of pyroxene. So when your rover sees surfaces where low-calcium pyroxene and olivine dominate, and plagioclase is much less common, that's a strong hint that you're not just looking at typical crustal rock anymore. You might be looking at fragments that came from deeper inside. In other words, the spectrometer is acting like a chemical fingerprint scanner. If those interpretations are right, Yutu-2 is rolling over material that was once part of the moon's mantle, material that an enormous impact ripped up and dumped into the basin. You're still only seeing the top few centimeters, but the composition is whispering, this started much deeper. So what does it actually buy you if you're sampling the mantle this way? What can those rocks tell you that crustal rocks can't? Mantle-type rocks give direct clues about the moon's bulk iron content, its early layering, and how its original magma ocean cooled and separated. After the moon formed, it was likely mostly molten. As that global magma ocean cooled, heavier minerals like olivine and pyroxene would have crystallized first and sunk, forming a dense mafic mantle. Lighter minerals rich in aluminum and calcium like plagioclase would have floated upward, forming a lighter crust on top. If U22 is really seeing rocks rich in olivine and low calcium pyroxene near the surface, that supports this picture. It says, yes, there is a dense mantle layer made of these minerals, and yes, big impacts can dig it up. That helps you lock down how thick the crust is, how dense the mantle is, and how sharp the boundary between them might be. Those details sound small, but they feed straight into how the moon's gravity field looks, how heat moves inside it, and how easily magma can rise. There's another layer to this. The exact mix of minerals and how much iron they contain tells you how the moon separated from Earth in the first place. If the mantle is more iron-rich or less iron-rich than expected, that changes how you tune the computer simulations of the moon's birth and evolution. So these rocks are not just interesting, they're constraints, hard limits on which origin stories are even possible. That leads to a larger, more technical tension. How do these new mantle clues force us to rewrite the big computer simulations of the moon's birth and evolution? Every serious simulation of the giant impact has to make choices. How big was the impactor? What angle did it hit at? How much mixing happened between Earth's material and the impactor's material? How fast did the moon cool? How stiff was its mantle over time? And how easily it start and stop convecting? You can tweak those parameters and still get a moon in the computer, but not all those moons will match the real one. Before Chang'e 4 and its Yutu-2 rover, those models were heavily tuned to Apollo-Gera data from one hemisphere. They had to match the near-side crust thickness, the overall density, and the chemistry of the rocks we had. Now, with possible mantle-derived material exposed in the South Pole Aitken Basin, you get extra targets to hit, the mineralogy and inferred composition of the deep interior on the far side. If your simulation produces a moon whose mantle is too iron-poor or too stiff, it won't match the U22 fingerprints. If it spreads heat-producing elements evenly instead of letting them clump under regions like Oceanus Procellarum, it won't match the thermal story told by Chang'e 5. So these new data act like a filter. Many older, simpler models get thrown out, and only the ones that produce the right kind of mantle, the right kind of crust, and the right long-term heat pattern survive. All of this narrows in on one clear message. The moon is not a uniform ball of rock. It's a layered, asymmetric body, scarred by at least one giant impact that dug deep into its interior and brought pieces of its mantle to the surface, where we can read them with rovers and lab instruments. And that cranks up the next question in the chain. If the moon has two faces and a warped interior, and we now see that directly in mantle fingerprints and thermal history, what happens when we compare the near side and far side more systematically and ask just how different these two hemispheres really are? How can one moon show you two completely different worlds and still pretend it's a single object? When you look up from Earth, you only ever see one face, the near side. It has big, dark lava plains, the Maria, surrounded by bright, rough highlands. For a long time, that one face dominated our thinking because that's where Apollo landed, that's where the Soviet Luna missions landed, and that's where Chang'e 5 landed. All the really detailed rock stories came from this single hemisphere, so the near side quietly became the moon in people's heads. The far side tells a totally different story. Once orbiters started mapping it, it was obvious. Almost all bright highlands, almost no broad dark Maria, more deep craters and huge basins. It looks older, rougher, and less resurfaced. Then NASA's Grail mission mapped the moon's gravity in detail and turned that visual difference into hard numbers. On average, the far side crust is about 20 kilometers thicker than the near side, roughly 60 kilometers versus 40 kilometers, so about 37 miles versus 25 miles. That means one hemisphere has a thinner shell over the mantle, the other has a thicker, tougher lid. So right away you get this uncomfortable mismatch. We built our main moon story from the thin, volcanic side and then tried to apply it to a thicker, quieter far side that we had never sampled. It was a classic bias. Everything was based on the hemisphere that happened to face us. The real test had to come from actual rocks. As long as a far side was just pictures and gravity maps, you could argue maybe it just looks different. Maybe the underlying mantle is basically the same. Maybe volcanism just didn't happen to break through as often. You could always hide behind, we just haven't landed there yet. Chang'e 6 killed that excuse. By landing in the South Pole Aitken Basin on the far side and bringing back about 1.9 kilograms, around 4.3 pounds, of soil and rock, Chang'e 6 finally gave labs on Earth physical material from that hemisphere. When scientists started analyzing the basalts in those samples, they were looking for the same kind of clues as with Chang'e 5: formation temperature, composition, crystal structure, traces of water, and other volatiles. The key number that jumps out is the crystallization temperature. The far side basalts from Chang'e 6 formed at around 1100 degrees Celsius, roughly 2000 degrees Fahrenheit. Comparable near-side mare basalts of similar age typically crystallize closer to about 1200 degrees Celsius, around 2200 degrees Fahrenheit. That's a temperature gap of about 100 degrees Celsius, around 180 degrees Fahrenheit, for magmas that formed at roughly the same time in two different hemispheres of the same body. That difference sounds small in everyday terms, but in mantle physics, it's huge. It means the mantle feeding the far side eruptions was genuinely cooler, not just less lucky at producing lava. You're not dealing with random chance. You're dealing with a systematic thermal difference. The far side is not only thicker at the crust level, it's also colder in the upper mantle under that crust. So now you can't dodge the conclusion anymore. The moon really is two-faced on the inside, not just on the outside. When you combine the Chang'e 6 temperature data with Grayle's crust thickness map, a clear pattern emerges. On the near side, the crust is thinner on average, around 40 kilometers, about 25 miles, and there's strong evidence from geochemical mapping that heat-producing elements like uranium, thorium, and potassium are concentrated under regions like Oceanus Procellarum. That extra radioactive heating, over billions of years, keeps the near-side mantle roughly 100 to 200 degrees Celsius warmer than the far side. On the far side, the opposite is true. The crust is thicker, around 60 kilometers, about 37 miles, which makes it harder for magma to punch through, and the mantle beneath it appears to be poorer in those heat-producing elements, so it cools faster and stays more rigid. Add those two factors, less internal heating and a thicker, stronger lid, and you get fewer eruptions, fewer mare basalts, and a surface that stays dominated by highlands and impact scars. In blunt terms, one hemisphere has a hot engine under a thin shell. The other has a cooler engine under a thick lid. That's not a subtle tweak. That is a global-scale structural asymmetry baked into a world only 3,475 kilometers wide, about 2,160 miles. The moon stops being a simple ball of rock and becomes a lopsided system with its own internal rich side and poor side in terms of heat and volcanism. This also feeds back into everything you heard from earlier sections. Chang'e 5's young lava, around 2 billion years old, already told you the near-side mantle stayed hot for a long time. Chang'e 4 and Yutu-2's measurements in the South Pole Aitken Basin on the far side hinted that deep mantle material might be visible at the surface on the far side. Chang'e 6 now adds, and that far side mantle is cooler and drier when it does melt. Put together, that's a three-point line that locks in the asymmetry, thermally, chemically, and structurally. Now the stakes go beyond just the moon. Once you accept that a single small body can naturally evolve into two very different hemispheres, you suddenly have a test case for every other lopsided world you've seen. Take Mars. The northern hemisphere is low and relatively smooth. The southern hemisphere is higher, thicker crust, and heavily cratered. That's called the Martian crustal dichotomy. There is still debate whether a giant impact, internal convection patterns, or a mix of both caused it. The near-far side split with a huge impact basin on one side and concentrated heat sources under the other gives you a real example to compare against, not just theory. Look at Pluto. One side is dominated by a bright heart-shaped region called Sputnik Plania, a deep basin filled with exotic ices, connected to strange internal dynamics. The other side looks different. On exoplanets, you can have permanent day and night sides, especially on worlds close to their stars, where one hemisphere faces the star constantly and the other is locked in darkness. Those planets are almost guaranteed to have wild temperature differences, different atmospheric behavior, and maybe even different crustal structures between hemispheres. The moon, with its hot near side and cool far side, becomes a reference model. It shows that you don't need an atmosphere or a strong current heat source to get global asymmetry. You can get it from how heat-producing elements are distributed, from where giant impacts hit, and from how crust thickness and mantle temperature interact over billions of years. It turns the moon into a kind of minimum case lopsided body, as simple a system as you're likely to find that still shows a dramatic two-phase structure. So now the pressure ramps up again. You're holding rocks and gravity maps from a body that clearly did not cool in a uniform way, that clearly did not erupt in a symmetric way, and that clearly did not keep its heat sources spread evenly. The moon is telling you, directly, that global asymmetry is not rare or exotic, it's a natural outcome given the right early conditions. That leads to the next hard question. If one hemisphere of the moon ended up hotter and more volcanic, and the other ended up thicker and cooler, what set that up in the first place? And is there a single ancient event big enough to explain both the crust thickness and the temperature split in one shot? How much of what you see on the moon today is just fallout from one hit right at the start? You've already seen that the moon has a hot, thin-crusted near side and a cooler, thick-crusted far side. That's weird on its own, but it gets more interesting when you ask a simple question. Did something early on kick the whole body into this lopsided state, and did it stay that way for the next 4 billion years? That's where the South Pole Aitken Basin comes in. On the far side, wrapped around the South Pole, there's a single impact structure about 2,500 kilometers across. That's almost a quarter of the moon's total circumference. In miles, that's around 1,550 miles wide. Depth estimates go up to roughly 8 kilometers in places, around 26,000 feet. This is not a regular crater. This is a basin that covers a big fraction of an entire hemisphere. Dating puts its formation at around 4.3 billion years ago, very early, when the moon was still young and hotter inside. So here's the key tension. If this thing is that big and that old, did it just leave a visible scar on the surface, or did it actually reconfigure the moon's interior, stripping and reshuffling material on a global scale? To answer that, you need chemistry, not just pictures. That's where Chang 6 becomes critical again. Chang 6 landed inside this basin, grabbed about 1.9 kilograms, roughly 4.3 pounds, of soil and rock and sent them back to Earth. When labs started analyzing those grains, one of the things they looked at was potassium, specifically the relative amounts of two stable isotopes, potassium-39 and potassium-41. You don't need the exact nuclear physics, just the pattern. High-energy events and extreme heating can change the balance between these isotopes by driving off lighter or more volatile species. In the Chang 6 material, the ratio of potassium-41 to potassium-39 is shifted compared to what you'd expect from more normal lunar rocks. That shift lines up with what you'd expect from very intense heating and volatile loss. In other words, you're not just seeing random variation, you're seeing a chemical pattern that says this stuff was cooked hard in a violent event, and some of the more easily lost material was stripped away. That's a direct chemical scar from the formation of the South Pole Aitken Basin. For a short period, part of the crust and upper mantle there were heated so much that volatile elements, including some forms of potassium, and probably some associated water and other light elements, were driven off or redistributed. You're reading that history from the potassium isotopes locked in those grains 4.3 billion years later. So what does one insane collision like that actually do to a small world? Think through the chain. You slam a huge impactor into one hemisphere. You excavate deep rock, you melt and even vaporize large volumes of crust and mantle, and you throw material out across the moon and into space. In the region around the basin, you strip volatiles and likely reduce the concentration of heat-producing elements in the material that cools and becomes the far side crust and upper mantle. That means fewer radioactive sources like uranium, thorium, and potassium left in that hemisphere to keep it warm over time. At the same time, a lot of the melt and ejecta can be redistributed, not evenly, but preferentially. Some models suggest that material rich in heat-producing elements may have flowed or been in place toward the opposite hemisphere, the near side. Over long timescales, that concentrates the internal heating fuel under the side that faces Earth and leaves the far side relatively depleted. Now connect that to what you already know. The far side ends up with a thicker, more rigid crust, around 60 kilometers, about 37 miles, and cooler basalts that crystallize at lower temperatures. That fits with having fewer heat-producing elements and less internal heating. The near side ends up with a thinner crust, around 40 kilometers, about 25 miles, and a mantle that's hotter by roughly 100 to 200 degrees Celsius compared to the far side, feeding extended volcanism and big lava plains. So one impact 4.3 billion years ago doesn't just make a big hole. It helps set up which hemisphere has the thermal fuel, which hemisphere has the thin lid, and which hemisphere gets most of the lava later on. That's a world being reshaped from the inside out by a single event. Here's the key point. This is not just a nice story. The potassium isotopes in Chang'e 6 samples, the crust thickness from Grail, the different lava temperatures between near side and far side, and the distribution of thorium and other heat-producing elements all lean in the same direction. The far side, and especially the South Pole Aitken Basin region, is chemically and thermally marked as a place that got stripped and cooled faster. The near side looks like the side that inherited more of the long-term heat. So now pull back. Why does this matter for anything beyond the moon? Because this gives you a concrete example of how a single giant impact early in a body's history can set up a permanent internal asymmetry. The basin is about 2,500 kilometers, 1,550 miles. On the moon, that's almost a quarter of the circumference. On a larger planet, a similar relative impact would be even bigger in absolute terms. If a super-Earth gets hit by something that opens a basin that large, the energy involved will dwarf what we're talking about here. For exoplanets, especially those we only see as dots or as dips in starlight, we can't map the basins directly yet, but we will see lopsided behavior. Temperature differences between hemispheres, one side with more volcanism or more outgassing, or different atmospheric composition. Right now, we can only guess which combinations of early impacts and internal dynamics could create those patterns. The moon, with its South Pole Aitken Basin and its clear near-far side split, gives you a test case with numbers attached. Same for Mars. If a single hemisphere scale impact helped create its crustal dichotomy, the moon is your smaller practice run. Same for any outer solar system moons that show big basins and weird local heating. The basic idea is the same. One massive collision can rearrange where heat sources sit, how thick the crust is, and how easily magma can rise. And those changes can last for billions of years. So you're no longer looking at giant impacts as just crater makers. You're looking at them as architects of entire interiors. The South Pole Aitken Basin is your proof that a single event can help decide which side of a world stays volcanically alive and which side locks up. And that pushes you straight into the next question. If one hemisphere got stripped and cooled and the other stayed hot, how does that show up when you actually take the moon's temperature directly, comparing near-side and far-side lavas and mapping heat at the global scale? How do you actually prove that one half of the moon runs colder than the other, when all you have are rocks and gravity? Start with the rocks. Chang'e 6 landed on the far side, inside the South Pole Aitken Basin, and brought back basalts that formed around 2.8 billion years ago. In the lab, scientists look at the minerals in those basalts and the tiny inclusions inside them to estimate the temperature at which the magma crystallized. For the Chang'e 6 samples, that crystallization temperature comes out to roughly 1,100 degrees Celsius, about 2,000 degrees Fahrenheit. Now compare that to basalts of similar age from the near side, from Apollo and from Chang'e 5. Those typically crystallize closer to about 1,200 degrees Celsius, around 2,200 degrees Fahrenheit. So you're not talking about a random spread. You're seeing a consistent gap of about 100 degrees Celsius, roughly 180 degrees Fahrenheit, between far side and near side magmas of similar age. That difference is baked into the rocks. It's not a model, it's not an assumption, it's a direct reading of how hot the melt was when it started to turn solid. And because magma takes its temperature from the mantle that produced it, those basalts are telling you that the mantle feeding the far side eruptions was running cooler than the mantle feeding the near side eruptions at the same point in time. So the first part of the picture is simple. Same moon, same age window, but different lava temperatures. Cooler on the far side, hotter on the near side. The next question is, does that local rock evidence line up with the global whole moon picture of what the interior is doing? That's where GRAIL comes in. NASA's GRAIL mission flew 2 spacecraft around the moon, measuring tiny changes in their separation as they were tugged by variations in the moon's gravity field. From those gravity variations, you can infer how mass is distributed inside, how thick the crust is in different places, and how dense the underlying mantle is. GRAIL confirmed that the far side crust is thicker on average, about 60 kilometers, roughly 37 miles, compared to about 40 kilometers, around 25 miles on the near side. But gravity data can also be combined with models of how rocks behave at different temperatures to estimate relative mantle temperatures. When you do that, you get a consistent result. The mantle under the near side mare regions is warmer by on the order of 100 to 200 degrees Celsius than the mantle under the far side. So now you have 2 independent lines of evidence pointing in the same direction. The rocks say far side lava was cooler by roughly 100 degrees Celsius at a given age. The gravity and interior models say the mantle under the near side is hotter by about 100 to 200 degrees Celsius overall. Together, they describe one hemisphere with a hotter mantle under a thinner shell, and another with a cooler mantle under a thicker lid. At this point, it's natural to think, okay, 100 degrees Celsius difference across a body 3,475 kilometers, about 2,160 miles, doesn't sound dramatic. Earth's surface swings more than that between a hot desert day and a polar winter. So does that temperature gap really matter deep underground? For mantle rock, it absolutely does. The material we're talking about isn't liquid like water, and it isn't hard like cold concrete. It's solid rock that can slowly deform over long timescales if it's warm enough. The key is how close that rock is to its melting point, and how easily its crystal structure lets it flow under stress. Raise the temperature by 100 degrees Celsius in that regime, and the rock becomes much softer over geological time. It'll creep more easily, convect more readily, and generate melt in certain pressure ranges. Drop the temperature by 100 degrees, and you move it further away from conditions where partial melting starts, and you make it more rigid. In simple terms, on the warmer side, the mantle behaves more like very slow, soft putty. On the cooler side, it behaves more like a brittle, locked shell. That's directly tied to volcanism. In the near-side mantle, with extra heat from concentrated radioactive elements and a thinner crust above, it's easier for rising melt to form, gather, and punch through to the surface. You get extended periods of lava flooding the low areas, filling basins, creating the dark Maria that you can see with your naked eye. On the far side, that same 100 to 200 degree deficit, plus a thicker, stronger crust, makes it harder for melt to form at all, and harder for any melt that does form to escape. The result is far fewer large lava plains, even over billions of years. So that 100-degree difference is not a cosmetic detail. It's a switch. One hemisphere gets a long volcanic life, the other locks up early and stays mostly frozen. Once you accept that the moon has this built-in thermal asymmetry, you no longer have the option of using simple one-dimensional models where the moon is treated as a uniform sphere that just cools down evenly with time. Those models assume the same temperature at a given depth in every direction, the same heat production everywhere, and a crust that just gets a bit thicker as you go around. Chang'e samples and the GRAIL data force you to drop that picture. Instead, you need 3-dimensional simulations where heat-producing elements are unevenly distributed, with higher concentrations under regions like Oceanus Procellarum on the near side and lower concentrations under the far side highlands. You have to include the effect of giant impacts like the South Pole Aitken Basin, which can strip volatiles and reshape where certain elements end up. You need a crust whose thickness varies by tens of kilometers, with real consequences for how magma rises and where it can erupt. The Chang'e 5 and Chang'e 6 rocks give you specific temperature anchors at specific times: 2 billion-year-old hot near-side lava, 2.8 billion-year-old cooler far-side lava. Those anchors let you test your 3D models. If a simulation says the near-side mantle should have cooled below melt-producing conditions by 2.5 billion years ago, but your lab measurements show active lava at 2.0 billion, that model is wrong. If it predicts no significant temperature difference between hemispheres, but your basalts disagree by 100 degrees Celsius, that model is wrong too. So the moon goes from being a simple cooling ball in a textbook diagram to a complex asymmetric thermal system that you can now probe with numbers, not just guesses. And that has a ripple effect. Anytime you use lunar ages and crater counts to calibrate the history of other airless bodies, you now have to remember that the moon's own interior story is 3D and lopsided, not uniform and simple. That raises a new question that pushes a story into an even more sensitive area. If one side of the moon is hotter and more volcanic, and the other is cooler and drier, what does that do to something far more fragile than hot rock? The tiny traces of water and hydroxyl in the lunar soil that we used to think didn't exist at all. How can a world be called bone dry when its own dust quietly says otherwise? For years, the standard statement about the moon was simple: no air, no water, just dry rock and dust. Apollo samples seemed mostly water-free. Early instruments weren't sensitive enough to see tiny amounts, and it was easy to treat the moon as the dry control case in the solar system. That made the story clean. Earth is wet, the moon is dry. End of discussion. Chang'e 5 broke that simple picture. At the landing site, instruments measured the spectrum of sunlight reflected from the regolith, the loose soil on the surface. In that spectrum, you can look for a specific absorption feature caused by hydroxyl, OH, which is basically water with one hydrogen stripped away. Those in situ readings showed a small but clear OH signal. When you convert that into an amount, you get an average around 28.5 parts per million of water equivalent content in the regolith at that site. That number is tiny, but it's not zero. It means that out of 1 million units of soil by mass, only a few dozen units are water or hydroxyl. For a world you were told was totally dry, that's a direct physical contradiction. The dust itself is telling you there is trace water bound in or on those grains. So the next step is obvious. How small is small for water in terms you can actually picture? Think about a metric ton of lunar soil. 1,000 kilograms, roughly 2,200 pounds. With a content of around 28.5 parts per million, you're talking on the order of a few tens of milligrams of water equivalent per ton, a fraction of a gram in all that mass. That's basically nothing if you're thinking about drinking. You'd need tens of millions of kilograms of regolith to reach anything like a swimming pool's volume in water. But chemistry and engineering don't care about human intuition. They care about totals and energy. If you can mine huge volumes of regolith with heavy equipment and you have power to spare, even parts per million levels can add up. For making rocket fuel or life support oxygen, you don't need to drink that water directly. You can break it apart, use the hydrogen and oxygen separately, or combine it with other resources. At that point, the important question isn't, is this wet enough for a glass of water? It's, how much energy does it cost per kilogram of extracted water, and how much soil can I process per hour? So, near-side soils like those at the Chang'e 5 site are not wet in any everyday sense, but they are not empty either. They hold a thin, real layer of hydration that you have to account for if you ever want to use the moon as a resource base. That raises the next issue immediately. If the near side is this weakly hydrated, what does the far side look like? Especially in the scar of the South Pole Aitken Basin that was blasted and stripped by a massive impact. Far side soil from Chang'e 6 looks even drier. When scientists took a small sample, on the order of 5 grams, and measured its water content, they found less than about 1.5 micrograms of water per gram of soil. Put another way, that's under 1.5 parts per thousand by mass in milligram terms, and it sits at the very low end, or below, the 1 to 200 micrograms per gram range seen in many near-side materials. The exact numbers are small enough that you're dealing with the limits of measurement, but the direction is clear. The far-side regolith at that site holds significantly less water than typical near-side sites. That lines up with the bigger story you've already seen. The South Pole Aitken impact likely stripped volatiles like potassium and water from the far side crust and upper mantle, and the far side mantle stayed cooler and less active. Fewer heat-producing elements, fewer large eruptions, less opportunity to trap or recycle water in newly formed minerals. So now the moon's dryness comes with a split. Some regions are mildly hydrated, others are extremely dry. The far side, especially in this giant basin, looks like the side that lost more of its volatile budget early on. Now you have another question to deal with. Where does this tiny amount of water actually come from? And is it the same story everywhere? Chang'e 5's weak hydration signature fits a mixed origin. Part of it is probably solar wind implanted. The sun constantly throws out a stream of protons, basically bare hydrogen nuclei at high speed. When those protons slam into grains of a lunar dust, some of them can stick and some can react with oxygen in the minerals to form hydroxyl, OH, and in some conditions, actual water molecules, H2O. U22's measurements tell you how many particles are coming in, how many neutral atoms are flying back out, and how efficiently the surface is capturing hydrogen at different times and conditions. This is not a clean laboratory, it's a messy, continuous bombardment. But that's the point. You're seeing how a bare rock surface with almost no protection slowly changes its chemistry under relentless solar wind. That's the base layer of the moon's water story. Hydrogen from the sun, meeting oxygen in the rock, creating a thin film of new molecules right on the outer skin. Zoom in more. Each proton from the solar wind is moving at hundreds of kilometers per second, tens of thousands of miles per hour. At those speeds, a single impact is violent on the microscopic scale. It can shatter bonds, dislodge atoms, and even knock them completely off the grain and into space. Over millions of years, this doesn't just hit a few grains, it hits everything, over and over. The result is a nanometer-thick altered layer on almost every exposed grain, a skin only billionths of a meter thick. In that layer, atoms have been rearranged, hydrogen has been added, some elements have been depleted, and the optical properties change. That's why space weathering makes surfaces darker and redder over time. U22's data helps quantify this process, how much material gets sputtered away, how much hydrogen sticks, and how the balance shifts under different solar conditions. So the solar wind is both scrubbing and painting the moon at the same time, stripping material off while also implanting hydrogen and slowly building up hydroxyl and water on grain surfaces. The surface you see in a photo is not just ancient rock, it's rock that has been constantly reworked at the top few nanometers by this invisible rain of particles. Now put those microscopic changes into a global context. On Earth, water cycles through the atmosphere, clouds, rain, rivers, and oceans. On the moon, there is no air, no pressure to hold a gas blanket, and no liquid oceans. Here, water molecules, once formed, behave very differently. A water or hydroxyl molecule on the moon's surface can get knocked loose by a photon of sunlight, by a particle impact, or by thermal motion as the surface heats up during the day. Once freed, it doesn't drift in air. It follows a ballistic path, like a thrown ball, arcing up and then landing again somewhere else. It can bounce like this multiple times, jumping from place to place until either it breaks apart, escapes into space, or lands somewhere cold enough to trap it. The coldest places are permanently shadowed craters near the poles. Some of those regions never see direct sunlight. Their temperatures stay below 100 Kelvin, more than 170 degrees Celsius below zero, over 280 degrees Fahrenheit below zero. In those conditions, a water molecule that lands there can freeze and stay put for very long times. That's how you get polar ice deposits, microscopic or larger, built up over billions of years from molecules that started as solar wind hydrogen on sunlit grains far away. Chang'e 5's in situ spectrum, showing about 28.5 parts per million of water equivalent at its near side site, and U22's measurements of the solar-wind interaction on the far side are both parts of this cycle. They tell you how much hydrogen is being added, how much hydroxyl is present in one region, and they help constrain how fast water is being produced and how mobile it is on the surface. If you know the production rate and you know how efficiently the poles trap incoming molecules, you can estimate how long it takes to build up a given amount of ice in a shadowed crater. This is not just academic. If anyone wants to run a long-term base on the moon, especially a base that uses local resources instead of hauling everything from Earth, this solar wind-driven water cycle suddenly becomes part of an engineering problem. Say you want to crack water into hydrogen and oxygen, store the oxygen for breathing, and use the hydrogen and oxygen together as rocket propellant. You need to know two things very clearly: how much water is actually present in the regolith or ice deposits you're targeting, and how fast natural processes are replenishing that water, if at all. If you mine too quickly and the natural top-up rate is slow, you can deplete a deposit on human timescales. Solar wind is constantly delivering new hydrogen, but not at an infinite rate. The efficiency of turning that into stable water depends on surface temperature, mineral type, impact gardening of the soil, and how often molecules get a chance to hop toward the cold troughs without being destroyed. Chang'e 5 and U22 give you real numbers to plug into those calculations, not just rough guesses. They shrink the uncertainty on how much water you can expect per cubic meter of soil in certain locations, and how fast the system is being replenished. So when you hear parts per million of water or micrograms per gram of soil, it's easy to shrug. But behind those tiny numbers, there's a large-scale chemical machine, powered by the sun, that is quietly manufacturing, moving, and storing water-equivalent molecules across an airless world. And China's instruments aren't just proving that this system exists, they're starting to put hard limits on its speed and capacity. That leads straight into the next step if you're thinking about living and working out there. Knowing what happens in the top few nanometers and top few centimeters is not enough. To build habitats, park landers, and dig for resources safely, you need to know how the ground is layered tens to hundreds of meters down. On the far side, where you can't easily send big drills, how do you actually see that hidden structure and turn a rough landing site into a 3D map of what's under your feet? How do you really know what you're building on when you're standing on a surface that's been smashed and buried for billions of years? On the far side, U22 is answering that with radio waves instead of shovels. The rover carries ground-penetrating radar, and it sends pulses straight down into the subsurface. Those pulses bounce off layers with different densities and compositions, and the instrument listens for the echoes. From the timing and strength of those echoes, you can reconstruct what's happening tens, then hundreds of meters below the wheels. At the Chang'e 5 landing site in Von Karman crater, U22's radar has mapped structures down to around 300 meters deep, roughly 1,000 feet in depth, in metric, captured without drilling a single meter. The data show that the ground under the rover is not one simple layer of dirt on top of solid rock. Instead, you see multiple stacked units, some thicker, some thinner, some more reflective, some more transparent, all sitting on top of each other. So you are effectively getting a vertical slice through the moon, 300 meters tall, right under the far site surface. It really is like running a CAT scan on a world that you can't physically cut open. Every radar trace is a column of underground structure captured in meters and signal strength, not just in guesses about regolith depth. Once you start reading those profiles, a pattern appears. You see alternating bands that match what you'd expect from coarse, blocky ejecta and finer, more uniform material. Coarse layers likely come from big impacts that shattered rock and dumped broken blocks into the area. Finer layers can point to more mature regolith, slowly ground down by micrometeorites or lava flows that cooled into relatively uniform sheets. Put together, that means you're not looking at one lunar soil layer. You're looking at a stratigraphy, a layered history. Some layers record the time right after the South Pole Aitken Basin formed, when everything was chaos and big impacts were reshaping the region. Others record later impacts that added new ejecta on top. Others may record episodes when lava flooded in, cooled, and then got buried. Each major layer can correspond to a geologic event, a time when the local environment changed in a big way. The important part is that this history is encoded in depth and structure. A layer 30 meters thick, about 100 feet, means a very different event than a thin band only a few meters thick. By combining radar data with crater counts and other remote sensing, scientists can start dating and naming these layers, turning what used to be a patch of gray dust into a time sequence that stretches across hundreds of millions of years. Now think about how Yutu-2 is building this map. The rover doesn't just sit in one spot. It drives, slowly, cautiously, but it moves. As of 2022, it had covered on the order of 1,000 meters, about 0.6 miles. Later data extended that to more than 1.6 kilometers, roughly 1 mile. With every meter it travels, the radar keeps firing. That gives you a whole series of vertical slices, one after another, along the rover's path. When you line those slices up, you don't just see depth, you see layers tilt, how they thicken or thin out, where they are broken or displaced. You can tell if a blocky ejecta layer is continuous over hundreds of meters horizontally, or if it pinches out. You can see where lava might have pooled in low spots and where later impacts dug into older units. The more Yutu-2 crawls forward, the more of a 3D picture you get of the far side subsurface. This is why a slow-moving rover that only covers a kilometer or two can still be a huge win scientifically. Every single meter gives you a fresh cross-section down to 300 meters depth. You're turning a small traverse into a long underground profile, like laying out slices of the moon's crust side by side. Now compare that to a drill. A drill is great for bringing up physical samples, but it's limited in how deep it can go on a small rover. A meter, maybe a few meters, is already a big engineering challenge. Beyond that, it gets heavy and complex fast. Radar doesn't have that problem. With a compact antenna and electronics, you can probe hundreds of meters down, as long as the material is transparent enough for the frequencies you're using. For future bases, that difference matters. If you want to know where natural lavitudes might sit, you need to see hollow or low-density zones underground, tens to hundreds of meters below the surface. If you want to know how thick the loose regolith is at a possible landing site or construction site, you need to know where fine, low-density layers give way to denser, more solid rock. If you plan to bury habitats under a certain depth of soil for radiation shielding, you need to know if you actually have that much regolith, or if bedrock lies only a few meters down. Ground-penetrating radar gives you those answers in meters and density contrasts, not just in hopeful assumptions. It tells you if your planned base site sits on a thick cushion of loose material or a thin blanket over fractured rock. It alerts you to big buried blocks that could complicate excavation. It can even hint at hidden voids that you might exploit or need to avoid. So Yutu-2 is doing more than mapping the far side for pure science. It's turning the ground beneath a far side crater into a test case for how to see through the surface before you commit to heavy hardware and human crews. And that leads straight into the next very practical question. Once you know what's under your feet, how do you turn that knowledge into actual resources, oxygen, metals, water, and safe shelter so the moon stops being just a rock museum and starts acting like a usable outpost for the rest of the solar system? Why treat the moon as a museum piece when its dirt is literally made of the stuff you need to live and fly? Right under your boots, the lunar regolith is not just random gray powder. Chemically, it's roughly 40 to 45% oxygen by mass, locked up in oxides of silicon, iron, magnesium, aluminum, calcium, and a few other elements. The rest is mostly those metals themselves, plus trace elements. So when you look at a patch of soil, what you're really seeing is oxygen locked inside solid rock and the mix of metals that can be turned into construction material, shielding, wiring, and machine parts. The Chang'e 5 and Chang'e 6 samples matter here because they turn the global averages into local, real numbers. Orbital spectrometers and gamma-ray instruments can tell you, this region looks richer in iron, that region looks richer in titanium, but they're still at a distance. When you bring back kilograms of actual regolith and basalt, grind them, measure the exact oxide fractions, and compare that to the orbital data, you can calibrate the maps. You start to see which areas really are easier to mine for oxygen, which have more iron and titanium, which are more aluminum-rich, and which are poorer. That's a practical shift. Instead of the moon has oxygen in its rocks, you move to this specific plane has rock that will give you more oxygen per ton of soil and more iron per ton of slag than that other plane. For in situ resource utilization, ISRU, that's the difference between a vague concept and an actual mining plan with power budgets, extraction rates, and hardware designs. Then there's water, which you now know exists in tiny amounts almost everywhere, and in potentially larger amounts near the poles. Even if a site like Chang'e 5's has only tens of parts per million of water equivalent in the regolith, that small fraction adds up over large volumes. Take a square kilometer of surface, 1,000 meters by 1,000 meters, and assume you can work down 10 meters deep. That's 10 million cubic meters of regolith. Depending on density, you're talking on the order of 10 billion kilograms of material in that block. Now, apply tens of parts per million. You're into hundreds of thousands of kilograms of water equivalent if you can process that whole volume efficiently. Combine that with polar regions where orbital data suggest actual ice deposits in permanently shadowed craters, and suddenly the moon, 380,000 kilometers away, about 240,000 miles, starts to look less like a barren rock and more like a low-gravity fueling station. You don't haul all your propellant up from Earth's deep gravity well. You crack water on the moon into hydrogen and oxygen, chill it, and use it to fuel trips deeper into the solar system. This is not trivial. You need serious power, heavy processing equipment, and a detailed understanding of how variable the water content really is from place to place. That's where the combination of Chang'e 5's hydration measurements, Yutu-2's space weathering data, and future polar missions all interact. They turn, we think there's water, into here's the grams per kilogram, here is how it varies with depth, here is how fast solar wind can top it up. On top of oxygen and water, you have the heavier, more exotic elements. Near-side regions like the Procellarum creep terrain are known to be enriched in thorium, potassium, and rare earth elements. Creep stands for potassium, K, rare earth elements, Re, and phosphorus, P. Thorium and uranium are important because their radioactive decay produces heat, which is part of why the near-side mantle stayed warmer. But they also matter because in the long term, they are potential nuclear fuel. Right now, nobody is building a thorium reactor on the moon, but if you think in terms of a century-scale infrastructure, knowing exactly where thorium and other actinides are concentrated is valuable. It tells you where local nuclear power might be easier to set up, and where you might eventually extract fuel rather than exporting it from Earth. China's geochemical data from Chang'e 5 and Chang'e 6 help sharpen the maps of thorium and titanium abundance. Titanium itself, present as imilonite in many near-side basalts, is also a useful structural metal, strong and light compared to steel, and the clue to which basalt flows are more technologically interesting. So now you can start to see the moon as tiered resources. Regolith everywhere for oxygen and basic metals, hydration and ice as feedstock for air and fuel, thorium and titanium in specific regions as long-term power and high-performance materials options. The moon shifts from a place with interesting rocks into a testbed where you learn how to run an off-world industrial ecosystem. Then there's the question of where you actually put people and hardware, because raw exposure on the surface is a radiation and micrometeorite problem. This is where geology and engineering intersect again. Lava tubes, natural tunnels carved by flowing lava and later drained, are strong candidates for ready-made shelter. If you find a lava tube that's 20 meters high and 500 meters long, that's a tunnel roughly 65 feet tall and about a third of a mile long. Put a base inside that, and you've automatically got tens of meters of rock over your head, acting as radiation shielding and thermal insulation. China's orbital data, along with Yutu-2's radar profiles, feed into models that predict where these tubes are most likely to exist. thick, relatively young basalt flows with certain thickness and cooling patterns are good candidates. Radar can hint at voids and layered structures that match what you'd expect above and around lava tubes. Gravity anomalies can support or contradict those hints. The better your subsurface data, the more confident you can be that a potential tube is real, large enough, and structurally stable. So now resources and shelter stop being abstract. You can picture a specific site, a basalt plain with oxygen-rich regolith, trace water, nearby regions with higher titanium or thorium, and the lava tube 20 meters high, 500 meters long. In metric, you use meters and kilograms to design your excavators, your ISRU plants, your habitat volumes, your shielding depth. In miles and feet, you sanity check the scale in your head. A 65-foot tall tunnel, a third of a mile long with bulkheads and pressure halls inside, starts to look like a real base layout, not just concept art. All of this is why the moon is shifting in people's minds from a place you visit once to plant a flag into a place where you stress test every part of off-world living: mining, refining, power generation, construction, and closed-loop life support. And the data from China's missions, added to everything from Apollo, Luna, and other orbiters, are what let you put actual numbers on those plans instead of vague hopes. That pushes the story out even further, though. If the moon is turning into a resources testbed and a permanent outpost, it's not just about local geology. It's also about what kind of science you can do from there that you simply cannot do from Earth, starting with something the far side is uniquely good at: listening to the very early universe in radio frequencies that our own planet blocks. Why are cosmologists so interested in a quiet patch of dust on the far side of the moon when they already have giant telescopes on Earth and in orbit? Because for certain questions about the universe, especially about the time before the first stars switched on, Earth is a bad place to listen from. Your planet is loud. Radio stations, radar, satellites, power grids, all of that pours radio noise into space. On top of that, Earth's ionosphere blocks the very low-frequency radio waves you care about most if you want to study the cosmic dark ages, the era after the Big Bang but before the first stars and galaxies formed. The far side of the moon is different. When it's facing away from Earth, the bulk of the moon blocks almost all of our radio noise. There's no ionosphere, no atmosphere, no human transmitters, just raw space. It's the quietest place in the inner solar system for low-frequency radio astronomy. That silence is not just nice to have, it's a requirement if you want to detect faint signals near tens of megahertz, signals that carry information about neutral hydrogen filling the early universe. China has already proved you can land and operate there, more than once. Chang'e 4 put Yutu-2 down in Von Karman crater on the far side and used a relay satellite beyond the moon to keep contact. Chang'e 6 did the same in the South Pole Aitken Basin and brought samples back. That combination, landers on the far side and a relay in lunar orbit or beyond, is exactly the architecture you'd use for a serious cosmology radio array. You've gone from nice idea to this is logistically possible. So what does a serious array actually look like in this context, and why does the regolith matter? Think of taking a few square kilometers of flattish, far-side terrain, an area maybe 2 kilometers by 2 kilometers, and planting hundreds or thousands of simple dipole antennas directly into the regolith. Each dipole might only be a few meters long, but together they act as one giant listening surface. They'd be tuned to frequencies from about 10 to 100 megahertz. Those are wavelengths from about 30 meters to 3 meters long, scales where Earth's ionosphere is basically opaque. From Earth, you just can't do this. From the far side, you can. Those frequencies are where the 21-centimeter line from neutral hydrogen in the early universe gets stretched by cosmic expansion into the low-frequency band. By measuring how the average radio brightness changes with frequency, you're tracing how hydrogen went from a smooth fog to clumped structures, and when the first stars and black holes started heating and ionizing it. That's the cosmic dark ages and the cosmic dawn, and we have almost no direct data from that era right now. The antennas would be linked together, phased and calibrated to act like one synthetic telescope, and all their data would be sent back through a relay satellite, just like Qiao did for Chang'e 4 and like the relay for Chang'e 6. The fact that China has already landed 2 missions on the far side and kept them talking to Earth is the proof of concept for the communication side of this. The next step is to add a science payload that's basically just more ears in the regolith. But the moon isn't just a listening post for the very early universe. It's also a timekeeper for the violent history of the solar system. Every airless body gets bombarded by impacts. Over billions of years, craters pile up. If you want to know how old the surface is on Mars, or Mercury, or an asteroid, you count craters per square kilometer and then use the moon's record to convert that crater density into an age. That conversion is called the crater chronology. It relies on having some surfaces on the moon where you know both the crater density and the absolute age from rock samples. Chang'e 5's 2.0 billion-year-old lava flow is one of those anchor points. The South Pole Aitken Basin, at about 4.3 to 4.33 billion years old, is another, tied in part through sample analysis and in part through modeling and comparisons to other dated terrains. Together with Apollo and Luna ages, these Chinese results strengthen the ends of the moon's timeline, a very old, giant basin early on, and surprisingly young lava relatively late. That stretches and reshapes the crater density versus age curve. When you apply that updated curve to Mars, for example, some plains you thought were a certain age may shift. The same goes for volcanic regions on Mercury, or heavily cratered surfaces on outer moons. Small changes in the curve can move ages by hundreds of millions of years. That has direct consequences for when we think certain atmospheres thickened or thinned, when volcanic outgassing peaked, and how long liquid water may have persisted on or near the surface. Now, tie that to habitability. A world being constantly hammered by big impacts is a world where oceans are boiled off, crust is repeatedly melted, and any early biosphere gets wiped or reset. As the impact rate falls, windows open where surfaces can stay stable for long enough for complex chemistry to run, and maybe for life to start and get a foothold. If you sharpen the moon's impact history, you sharpen that whole picture. You can better say when Earth's own impact rate dropped to the point where stable oceans and crust could survive for hundreds of millions of years without being totally reset. That matters for our own origin of life timeline, and it matters when you think about Earth-like exoplanets. If you know how long a typical planetary system stays in a high-impact phase, you can estimate when it becomes realistically habitable, not just in terms of temperature, but in terms of stability. So China's rocks, pulled from a near-side lava plain and a far-side impact basin, end up doing double duty. At one level, they're telling you about local volcanism, mantle temperature, and impact scars. At another level, they're tightening the clock you use to date major episodes across the solar system, and they're helping define when planets like Earth stop being shooting galleries and start being good places for long-term oceans and life. Put all of that together, and the moon turns into something very different from the dead static object in old textbooks. It's a low-gravity platform for listening to the early universe, a calibration plate for impact history, and a stepping stone for understanding when life gets its chance on rocky worlds. And once you accept that the moon is this important as a lab and a clock, you have to ask a deeper question that sits underneath everything. If these new samples are reshaping how we see the moon's interior and its timeline, what do they do to the story of how the moon formed in the first place, and how tightly that story is tied to Earth's own early history? How do you upgrade the story of the moon's birth when every new rock sample keeps poking holes in the old script? For years, the main picture went like this. A Mars-sized body hits the young Earth early in the solar system's history. The collision is so violent that a huge amount of rock from both objects is blasted into orbit. That debris forms a hot, spinning disk around Earth, and over time, that disk clumps together and cools, becoming the moon. It's a clean idea, but all the hard details, impact angle, speed, how much of the debris comes from Earth versus the impactor, how much material escapes completely, all depends on what the moon is actually made of, how its interior is layered, and how many volatiles it managed to hang on to. Those things are not cosmetic. If the moon's bulk composition is almost exactly like Earth's mantle, you're looking at a very different impact scenario than if the moon is a 50-50 blend of Earth and some foreign body. If the moon ended up very dry in volatiles like water and potassium, that says the impact and the aftermath were extremely hot and efficient at boiling things away. If the mantle is strongly asymmetric, with heat-producing elements clumped under one hemisphere, that puts tight constraints on how the magma ocean moved and cooled after the impact. So the giant impact model isn't a single story, it's a family of stories. The job now is to use the chemistry and structure of the real moon to throw away most of those variants and keep the few that match reality. That raises the obvious question. How do you actually test these competing impact scenarios from 4.5 billion years ago when you can't replay the collision, and all you have are rocks and gravity maps today? This is where isotopes become your fine print. Elements like oxygen, titanium, potassium, tungsten, and others come in different isotopic flavors. Same element, slightly different mass. Different source bodies in the early solar system can have slightly different isotope ratios based on where and how they formed. When you compare isotopic ratios in Earth rocks and moon rocks, you're asking, how well mixed were the ingredients that built these two objects? Before Chang'e 5 and Chang'e 6, those measurements came mostly from Apollo and a few Soviet samples, all from the near side. They already showed that Earth and Moon are weirdly similar in some isotopes, especially oxygen, which pushed models towards impacts where the debris disk was very well mixed. But you still had gaps. No young basalts, no far-side material, not much leverage on how uniform that similarity was across the whole Moon. Now you add Chang'e 5's young near-side basalt, formed around 2 billion years ago, and Chang'e 6's far-side material from the South Pole Aitken Basin. You check oxygen isotopes, titanium isotopes, potassium isotopes, and more. If those new samples line up tightly with Earth's ratios, that reinforces the idea that the impact thoroughly mixed Earth and impactor material before the Moon condensed. If some isotopes show subtle differences, that tells you how much of the original impactor's identity survived in the Moon and how much volatile loss happened when the disk cooled. Potassium, for example, is useful because it's moderately volatile. The weird potassium 41 to potassium 39 ratios in Chang'e 6 material scream extreme heating and volatile loss in that region, consistent with South Pole Aitken being a scar from a huge later impact that cooked and stripped the far side. Oxygen and titanium isotopes, by contrast, are more about the original building blocks and mixing level of the Earth-Moon system. By combining all of these, you start cutting off large chunks of parameter space. Too little mixing, wrong. Too much leftover volatile, wrong. Wrong isotopic balance, wrong. But composition is only half the story. You still have to explain why the Moon ended up so lopsided inside. That's where the near-far side asymmetry you've been following turns into a hard constraint on origin models. Here's the core problem. Whatever formed the Moon had to set up conditions where heat-producing elements like uranium, thorium, and potassium ended up concentrated under the near side, especially under regions like Oceanus Procellarum, while the far side ended up with a thicker crust, fewer mare basalts, and a cooler mantle. That is not a random outcome. It points to specific flows in the global magma ocean, and specific ways dense and light materials separated as the Moon solidified. Some scenarios say the concentration of creep material, potassium, rare earths, and phosphorus, under the near side came from how the last dregs of the magma ocean, enriched in incompatible elements, got trapped and pooled on one hemisphere. Others suggest that after the Moon formed, a major impact, maybe South Pole Aitken itself, helped shuffle those elements, stripping volatiles and heat sources from the far side and leaving a relative excess on the near side. In both cases, the initial conditions right after the giant impact matter: spin rate, tilt, how quickly the disk cooled, how asymmetric the early crust was. The important part for you is this: you can't just pick any giant impact you like anymore. Your model has to hit multiple targets at once. It has to reproduce the bulk isotopic similarity between Earth and Moon. It has to explain the Moon's relatively low volatile content overall. It has to allow for a magma ocean that can generate a thick far-side crust and a thinner near-side crust. It has to give you a way to pile heat-producing elements under one hemisphere. And now it has to be consistent with the young 2.0 billion-year volcanism on the near side and cooler, drier volcanism on the far side at 2.8 billion years. If your simulation doesn't naturally create a lopsided thermal structure or can't keep parts of the near-side mantle warm enough for late volcanism, it's out. If it can't match the new isotopic data from Chang'e 5 and Chang'e 6, it's out. The Moon's asymmetry goes from being a curiosity to being a strict filter on which Earth-Moon origin stories survive. So why does any of this matter for Earth itself beyond the nice feeling of having a cleaner model? Because the way the Moon formed and evolved is directly tied to how Earth spins, how long our days are, how the tides behave, and how stable our climate has been over billions of years. The giant impact didn't just make the Moon, it also set Earth's initial spin rate and the amount of angular momentum in the Earth-Moon system. That dictates how fast the Moon moves away from Earth over time and how the length of our day has changed. If the impact was more head-on or more grazing, if more mass escaped or stayed bound, you get different initial rotation speeds and different tidal histories. A faster spinning early Earth with a Moon closer in would have huge tides and very short days. Over time, tidal interactions move the Moon outward and slow Earth's spin. The exact numbers matter because they influence how much energy is distributed between oceans and atmosphere and how sensitive the climate is to perturbations. Then there's obliquity, Earth's axial tilt. Large moons help stabilize that tilt against big swings. Mars, with tiny moons, has had its tilt wander dramatically. If the Earth-Moon system had ended up with a different mass ratio or a different distance trend, Earth's tilt could have been less stable. Large, chaotic swings in tilt can mean drastic climate swings, long ice ages, and unstable habitable zones. So when you tighten the constraints on the Moon's formation using Chang'e 5 and Chang'e 6 chemistry, you're also tightening the range of possible early Earth configurations. You're learning how much angular momentum the system really started with, how quickly the Moon must have receded, and how stable Earth's tilt likely has been. Those numbers are not abstract numbers. They feed into models of how long Earth has had relatively calm conditions where complex life could develop and endure. In that sense, the conditions for life on Earth are partially encoded in these Chinese moon rocks. The isotopes and element patterns they carry are not just telling you what happened to the Moon. They're telling you which versions of early Earth are plausible, how harsh the first few 100 million years were, and how quickly things settled into the slower, more stable patterns we rely on now. And that brings the story right up to your lifetime. If the Moon's origin, interior, water, and resources are all being rewritten right now, the obvious next step is this. What happens when humans go back, not just to visit, but to build, while this new science is still unfolding? How does this new picture of a hot near side, a cool far side, and a resource-rich regolith shape where we land, where we mine, and where we build the first real bases? How do you plan the next era of human spaceflight on a world whose basic story is changing while you're still designing the rockets? The next crews that step on the Moon are not going back to the simple, dead and dry Moon from old textbooks. NASA's Artemis missions are aiming for the South Polar region later this decade, hunting for ice in permanently shadowed craters and building the first infrastructure near the rim. China has announced its own goal of putting astronauts on the Moon around 2030. By the time those boots hit regolith, the picture of the Moon's interior, its water, and its resources has already been reshaped by Chang'e 5, 4, 5, and 6. That changes what a landing site even means. In the Apollo era, you mostly thought in terms of safety, lighting, slopes, and surface hazards. Now, every potential site also has a data stack behind it. Regolith thickness in meters, hydration in parts per million, rock chemistry in oxide weight percent, subsurface layering down to hundreds of meters. You're sending people into a data-rich environment. They aren't discovering the Moon from scratch. They're ground-truthing a detailed model built by robots. So where do you put those first long-term bases if you want them to pay off scientifically and operationally? Far-side samples from Chang'e 6 tell you that part of the moon's interior is cooler, drier, and stripped of heat-producing elements. That makes regions inside the South Pole Aitken Basin prime spots for studying the deepest, oldest impact scars and for sampling possible mantle material directly, but less attractive if you want lots of easy volcanic rocks or higher water content. Near-site sites like the Chang'e 5 region with young titanium-bearing basalt and extended volcanism down to 2 billion years old are the opposite, perfect for probing long-lived mantle heat and resource-rich mare, but not as extreme in terms of ancient impact history. Simply put, you now have a menu. You can send a crew to a spa melt site to walk on rock that records a 4.3 billion-year-old trauma and contains clues to mantle composition. You can send another to a young mare unit to chip and drill through 2 billion-year-old lava and directly test how long the moon's interior stayed active. Each mission can be tuned, more geology, more resources, more radio-quiet science, depending on what you prioritize. On top of that, the South Polar region that Artemis targets is no longer just interesting because of possible ice. It sits at the crossroads of several gradients: sunlight versus permanent shadow, warm versus ultra cold, possibly hydrated regolith versus almost pure ice deposits. Chinese and other orbital data give you maps of where permanently shadowed regions begin, where slopes are manageable, and where hydrogen signatures are strongest. You're not guessing where the ice might be. You're selecting ridges and crater rims where a base can sit in sunlight a few kilometers from potential ice-rich coal traps. And this is where the engineering side locks on to the science side. All the numbers you've heard, regolith density, hydration levels, layer thicknesses, feed directly into machine design. If radar and sample analysis say the regolith at your chosen base site averages 5 meters thick, roughly 16 feet, over competent rock, you can design excavators sized to move that amount of material for shielding, and drills that only need to penetrate that depth to anchor foundations. If another site has 20 meters of loose regolith, about 65 feet, before you hit solid rock, that's a completely different class of machine. More power, more mass, more wear, more risk of getting stuck. Engineers don't just ask, can we land there? They ask, what does the first kilometer of trenching look like in cubic meters and kilowatt hours? The same logic applies to ISRU plants. If you know regolith at one site holds 30 parts per million of water equivalent and at another holds 10, that changes your throughput requirements. At 30 ppm, you need to process about 33,000 kilograms of soil to get 1 kilogram of water. At 10 ppm, you need 3 times that, about 100,000 kilograms. That's not a small tweak. That's the difference between a pilot plant and an industrial-scale factory if you want the same water output per day. Chang'e 5 and Chang'e 6 data don't just inform geology papers, they set the denominator in these equations. And you're not designing in the dark. U22's ground-penetrating radar has already shown that some far-side sites have stacked ejecta and rock blocks down to 300 meters, about 1,000 feet. That tells you how heterogeneous the ground can be. Zones where a drill will chatter on buried boulders. Zones where a tunnel boring machine might hit fractured ejecta instead of clean basalt. You can match that to orbital lava flow thickness maps and pick base sites with the right balance of stability, resources, and science value. All of this changes your role in the story. You're not just watching distant agencies make plans. You're living in the window where these decisions are locking in. Right now, data from China's missions are flowing into shared scientific literature, into international models of the moon's crust and mantle, into resource maps, and into risk assessments for human missions. When planners decide which crater rim to target, which mare patch to sample, which lava tube candidate to survey for a habitat, they're using those numbers in the background. 2.0 billion year lava dates, far-side hydration limits, regolith densities, thorium and titanium maps. If you're under 40 today, you have a very high chance of seeing the first long-term lunar base go from sketches to construction, with people living there for months or years at a time. That base will not be placed randomly. It will be anchored on top of the same kind of data you've been hearing about. Chang'e 5's young basalt, Chang'e 6's far-side chemistry, Yutu-2's subsurface scans, plus whatever Artemis and other missions add. So the tension now is simple and sharp. With all of this new information, the moon is no longer just a target, it's a roadmap. The only real question left is, now that China's missions have forced everyone to redraw that map, what exactly does China's moon discovery changes everything mean for how you think about time, interiors, water, and the future beyond the moon itself? So, what does it actually mean in concrete terms when you say China's moon discoveries change everything? First, it hits the timeline. You no longer live with a moon that switched off early and politely stayed dead. The picture you grew up with said, most volcanism ended by around 3 billion years ago, youngest lava about 2.8 billion years ago. That was nice and tidy. Chang'e 5 samples smash that. Those basalt are about 2.0 billion years old, and they're not a tiny leftover drip. They're a whole lava unit tens of meters thick, hundreds of kilometers across, with a volume in the thousands of cubic kilometers. That's a serious eruption, happening when the moon was already more than halfway through its life. Then, Chang'e 6 adds another twist. Far-side basalts around 2.8 billion years old, but crystallizing at cooler temperatures, about 1,100 degrees Celsius, roughly 2,000 degrees Fahrenheit, instead of the hotter 1,200 degrees Celsius, about 2,200 degrees Fahrenheit, typical of similar age near-side lavas. Put that together and you're forced into a new timeline. Volcanism doesn't just taper off nicely at 3 billion years. It drags on to 2.0 billion years in some regions, while other regions are already cooler and quieter. Thermal evolution models that used to show a smooth, fast cooling curve now have to stretch, bend, and develop a long tail of late, regionally focused activity. The moon didn't die early, it cooled in slow motion, and it cooled unevenly. Second, it changes the interior from something simple to something awkward and lopsided. You can't pretend the moon is just a symmetric ball of rock with a thin crust and a uniformly cooling mantle. The data now say thinner crust on the near side, about 40 kilometers, roughly 25 miles, thicker crust on the far side, about 60 kilometers, around 37 miles. Mantle under the near side warmer by roughly 100 to 200 degrees Celsius. Mantle under the far side cooler. Heat-producing elements, uranium, thorium, and potassium, are more concentrated under the near side mare, especially in regions like Procellarum creep terrain. On top of that, you have the South Pole Aitken Basin, about 2,500 kilometers across, around 1,550 miles, likely formed around 4.3 to 4.33 billion years ago. That one impact appears to have stripped volatiles and some heat sources from the far side crust and upper mantle, while leaving a relative excess on the near side. So the interior is not just layered core mantle crust, it's layered and skewed. One hemisphere with a hot engine under a thin lid that kept feeding lava for billions of years. One hemisphere with a cooler engine under a thick, rigid shell that locked up much earlier. Any model that still treats the moon as radially symmetric is wrong by design now. Third, it rewrites the water story in a way that's very specific and very inconvenient for the old airless and dry line. Chang'e 5's spectra at the landing site show around 28.5 parts per million of water equivalent in the regolith. That's only a few milligrams of water per metric ton, 1,000 kilograms, roughly 2,200 pounds, of soil, but it's real. Chang'e 6's far-side soil looks even drier, less than about 1.5 micrograms of water per gram, clearly on the low end compared to many near-side samples. So instead of a wholly dry moon, or a simple there's ice at the poles, that's it picture, you now have a patchy system, near-side mid-latitudes with tens of ppm hydration from a mix of solar wind implanted hydrogen and native water trapped in minerals. Far-side regions, especially inside South Pole Aitken, even more stripped with very weak hydration. Polar cold traps potentially holding much larger deposits built over time from molecules hopping across the surface in ballistic jumps. Water on the moon stops being a yes-no question and becomes a map, where it's present, in what form, at what concentration, and how it moves under solar wind, temperature swings, and impact gardening. Fourth, it changes how you date everything else in the inner solar system, even if that shift is quiet and technical. Ages for surfaces on Mars, Mercury, Vesta, the Galilean moons, anything airless or nearly airless, are mostly built by crater counting. You measure craters per square kilometer, then use the moon's known ages to convert that crater density into an absolute age. Chang'e 5's 2.0 billion-year lava becomes a late anchor point, a surface with a known age and a known crater density. The South Pole Aitken Basin, at about 4.3 to 4.33 billion years, locks in an extremely old end of the scale. When you add those points, the crater chronology curve changes its shape, especially in the middle and late time ranges. That means some Martian plains, previously labeled with one age, now shift by hundreds of millions of years. Same for volcanic fields on Mercury or resurfaced patches on big moons. Geological eras, Noachian, Hesperian, Amazonian on Mars, for example, can slide in time. The timing when bombardment declined, when volcanism peaked, when surfaces stabilized enough for long-lived environments all get nudged. You don't see those changes in the night sky, but they live in every diagram, every timeline, every "this happened X billion years ago" sentence tied to cratered worlds. Finally, it changes what comes next in a very practical way. These discoveries don't just sit in papers, they feed directly into what humanity does with the moon and beyond. Knowing the moon stayed volcanically active to 2.0 billion years and that heat sources are concentrated under the near side tells you where to go if you want to study long-lived mantle activity in person. Knowing the far side is cooler, drier, and structurally different tells you where to sample ancient impact melts, mantle material, and build radio telescopes in the quietest radio environment you can get. Resource maps based on Chang'e 5 and Chang'e 6 chemistry steer where you try serious ISRU first, which may have oxygen-rich regolith and useful metals, which polar regions are more promising for ice extraction, which flows have titanium content worth exploiting. Interior models constrained by Chinese and earlier missions rewrite the inputs for giant impact simulations, which feed back into how you think Earth's early spin, tides, and climate evolved, and how long stable, life-friendly conditions really lasted. Even cosmology and exoplanet science feel it. A reliable lunar impact chronology tightens the window for when Earth stopped being a shooting gallery, and when oceans and early life could persist without constant reset. A Farsight probe as a radio-quiet accessible platform sets the stage for low-frequency arrays listening to the cosmic dark ages. That, in turn, affects how you design future observatories, what frequencies you target, and how you plan international cooperation on the far side. So when you say China's moon discoveries change everything, you're not talking about a headline slogan. You're talking about a timeline that no longer lets the moon die early, an interior that cannot be treated as symmetric, a water system that is patchy and active at trace levels, a solar system age scale that has been quietly retuned, and a roadmap for future missions and bases that is now built on numbers instead of old assumptions. You're also talking about this happening while you're alive, before the first long-term bases are even built. The moon you send people back to in the 2030s is not the moon of Apollo. It's a more complex, more useful, more dangerous, and more interesting world, reshaped on paper by a few kilograms of rock and dust that robotic landers drag back across 380,000 kilometers of space. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.